Hey everyone, in this video, we'll show you how we solved the university timetabling problem using a constant satisfaction approach backed by a set solver. Let's dive in. Timetabling is basically assigning sessions like lectures, labs, etc. to time slots, rooms, students, and faculty members such that nothing overlaps. It's a classic constant satisfaction problem, and it gets tricky when you have lots of students, subjects, and limited resources. There are many real world constraints. For example, a faculty can't teach two subjects at once. A room can't host two lectures at once, and students cannot attend overlapping lectures. Practicals add another twist. They are often long and should be scheduled together. Before we move to the solution, let's look at the input data. So basically, our input data is four CSV files. First one contains student information, second file contains faculty and their subjects, third one contains room list, and fourth one is about student enrollments. So let's see why we should use CSP to solve this problem. It gives us a clean way to model all these rules, and modern set solvers make it scalable and super fast. That's what we'll show next. We model the problem as a CSV and then convert it to a set problem, and every possible combo becomes a Boolean variable like subject, type, day, slot, room, and faculty. Some key constraints are each subject has fixed L, T, and P hours. We ensure no overlapping use of rooms, faculty, or student time. For practicals, we try to place them back to back but allow flexibility if the constraint becomes too tight. Now let's have a look at the complete code. Before looking at the code, let's look at the input files. We load data from four CSVs. The first one contains information about the subjects. The second CSV file contains faculty and subject mapping. Third CSV file contains information of the rooms available for classes. And the fourth CSV file contains a student and the subjects they have enrolled in. We create Boolean variables for every possible assignment of a subject component to a day, slot, room, and faculty, and then do a variable mapping to include only the valid assignments. Moving on, we add the constraints. Each subject must get the required number of sessions for lecture, tutorial, and practicals. Second constraint is a room and a faculty cannot be double booked. Third constraint, third constraint is Third constraint is students cannot have overlapping sessions. We also try to keep practicals together but allow some flexibility if needed. Once the CNF is ready, we call the set solvers. It returns a valid model, we parse it and write it to the final output timetable file. Now let's have a look at the output that is generated. Now let us look at a Now let us have a look at the output timetable that is generated. The output CSV contains full schedule, subjects, day slot, time, room, and faculty. The output CSV contains full schedule, subjects, day, slot, room, and faculty information.
So hello everyone, I am Shivansh Kumar and in this project I have implemented a constraint-aware priority-based heuristic algorithm to generate a complete timetable for the spring semester of IIT Patna. The goal is to create a valid timetable that schedules all courses, lectures, tutorials and practicals while satisfying various hard constraints like room availability, student and faculty clashes and practical continuity. My approach uses a heuristic algorithm that prioritizes subject based on their total load, number of enrolled students and presence of practicals. So let me walk you down through the step-by-step breakdown of the process. So the algorithm begins with pre-processing. It calculates the total load for each subject by adding lecture, tutorial, and practical hours. Then it counts how many students are registered for each subject and how many faculty members are assigned. Next, all subjects are sorted by priority. Those with higher loads, more students, and practical components are scheduled first. Then I initialize availability grids for rooms, faculty, and students. The time slots range from 8 a.m. to 6 p.m., excluding the lunch from 1 to 2 p.m. In the placement phase, the algorithm loops through each subject and tries to assign lecture, tutorial, and practical sessions, all while ensuring that no conflicts for student or faculty should occur. The room capacity should be sufficient, the practicals are scheduled in consecutive slots, and early morning or late evening classes are avoided as much as possible. So now let's talk about what constraints I have handled. So this heuristic ensures all hard constraints are respected, such as no student or faculty is double booked, room capacities are not exceeded, practical sessions are always consecutive, lunch hours are always free, and lecture tutorial formats like 3 is to 1 are properly handled. So at the same time, it tries to reduce soft constraints like gaps between the classes, switching off rooms frequently, and avoiding of 8 to 9 a.m. lecture or 5 to 6 p.m. lectures. So let me walk you down through the live demo of my project. So here is the implementation. I've implemented it with the pandas library, and if the uh, we are actually using the same CSV files as input to all the three different algorithms. Okay, so one has room availability, one has student subjects, one has the details about subjects, one has the detail about students. So all that same exact test case for all three algorithms, that is CSP, heuristic, and meta heuristic. So the same test case has been used here. And if I run this, so as we can see that our output is already generated, our timetable is generated, and what we can also see that it also outputs the timetable in the same directory as it is presented. So if we see that, so the subject schedule, it provides us the exact same timetable that was generated by this algorithm, and as we can see that there are no clashes, nothing, etc. So Uh, that was my heuristic based scheduling algorithm. It's fast and efficient, producing valid times tables for large data set, but compared to CSP or meta heuristic approaches, it may not always give the most optimized result. But it works well under practical time constraints and it is easy to implement. Therefore, for meta heuristic algorithm, I would like to call upon my friend Kijan to share his insights. Thank you.
Hi, my name is Kijen, and I will be explaining on the topic meta heuristic algorithm. So, what is meta heuristic algorithm? Meta heuristic algorithm are optimization techniques. They uses iterative search strategies to explore the solution space and find optimal or near optimal solutions. These algorithms use heuristic rules to guide the search and modify the solutions or iterations. And this meta heuristic algorithm, it basically has three types, and they are generative algorithms, simulated annealing, and particle swarm optimization. The stages of genetic algorithm. The first is the population. So what is population? Population is the collection of individual solutions, and the technical term for it is chromosomes. Each chromosome represents a complete timetable. First from first from the population. Okay, sorry. Break it down. Since I implemented the time scheduling using genetic algorithm, here is the brief explanation of genetic algorithm. Genetic algorithm are optimization techniques. They mimic the process of natural selection to evolve candidate solutions over multiple generations. Solutions are represented as strings of binary code, which are combined and mutated to produce new candidate solutions. The algorithm evolves the fitness of each candidate's solution based on a defined objective function and selects the fitness individuals for reproduction in the next generation. Genetic algorithms use operations such as selection, crossover, and mutations to create new solutions and maintains diversity in the population. As it is visible in this diagram, the first is population and then fitness. And after this, the selection, crossover, mutation. And if we don't obtain the optimal solution, then we perform we repeat the here is the steps of genetic algorithm. First is the population. Second, fitness, selection, crossover, mutation. And and after each iteration, we check for the optimal solution. If it is obtained, then we stop there. Else, we perform the next iteration. And the full explanation will be given with the code. Now I will explain the code. First, we initialize the constants. And the constants are time slots, days, and available slots. Available slots is the multiplication of the days and the time slots. CSV files. Here we read the files, the input files. Basically, they are the student, subjects, faculty, and the rooms. Pre-process. Here we store the data that we got from the input files. Genetic algorithm. Here we have declared the population size, generation, and mutation rate. Population size. It defines the chromosomes that is generated in each generation. And the generations is the iterations we performed to optimize the solution. Chromo- Chromosome representation. The chromosome is the now comes the chromosome representation. Each chromosome is a candidate solution. Fitness function is the fitness function evaluates how good a timetable is. It forms the matrix, and based on the goodness of the chromosome, it selects the most suitable candidate. Crossover. Crossover. Combine parts of two parent chromosomes. For example, swap half the subject schedules. And next is the mutation function. It randomly reassigns a subject slot, room, or faculty, ensures diversity in population, and prevents local optima. New generation replaces current population with the next generation.
So after running all those three algorithms on the same test case, we can conclude that each of these three approaches demonstrates different distinct strengths and trade-offs. So the SAT-based CSP method is best suited for strict constraint satisfaction and rapid timetable generation. The heuristic algorithm is valuable as fast baseline solution, especially for smaller instances or as an initial schedule for further refinement. The genetic algorithm excels in optimizing for multiple objectives and accommodating complex real-world requirements with higher computational cost. So we can see that SAT solver is conflict free. Heuristic is conflict free as well, but we need to do minor manual fixes. And the gaps between two different lectures for students was found to be medium in CSP, but very high in heuristic and low in genetic. Room switches were medium in SAT, but high in heuristic and lowest on genetic. And for early or late classes that we should try avoid, but it was a soft constraint, right? 8 a.m. classes or 5 p.m. classes, so it was few in CSB as well as genetic, but sometimes uh, we have that lecture has to take place in heuristic algorithm. So the computation time, SAT was the fastest, heuristic was in between the two, and it took minutes. But genetic algorithm, it took minutes. Very, very high computational power in that. And in terms of flexibility, heuristic algorithm is low flexibility. The SAT CSP solver has medium flexibility, but the genetic algorithm has high flexibility. So with this, we conclude our project. Thank you for watching.